Hello everyone. Today I'm going to solve a very interesting and popular programming interview questions. That's two sum. There are variations of this problem, but this particular one is a two sum problem in a given binary search tree. Right? Let's see what the problem is. So you are given a binary search tree. You can see one of the example input on the left of the screen, and you need to find two items. You need to make sure if there's any two node that exist in this binary search tree which sum up to a given target value 9. So in this case, we can see that 2 and 7 sums up to 9, so that we report that is true. There's just some number like that, right? Now here, for the same input, if you see the given target is 28, there's no way there can be two nodes that sums up to 28, because the smallest value what you can see is 2 and the largest is 7. So even the second largest what you see is 6, right? So is not there are there does not exist any nodes which sum up to 28 based on this input, like 7 and 6 sums up to 13, but that's the max what two nodes can sums up to. uh, the other thing to note here is this is a binary search tree. You might have encountered the same problem in an array, right? So if you are given an array and you need to find, like, you need to check if there are any two items in the array that sums up to a given target value. What we basically need to do is we go about sorting the array, right? You go about sorting the array, and then you start traversing array from the start and from the end simultaneously, and take the sum of the values pointed by the front and the head and the tail pointers, and see, like, if that sums up to the target, you find a solution. You found a solution. If the sum is smaller than the target, then you need to adjust the pointer. If it is smaller, you want to make sure, like, you reach a value that's bigger than current sum, so that it's closer to the target. So you shuffle the head pointer. And in the symmetrically opposite case, if the sum is greater than target, you want to take the sum to a smaller value so that it's closer to the target. For that case, since the array is sorted, you shuffle the tail pointer, right? So similar thing what we want to do here, but the data structure what you are given is not very linear. It's a hierarchical data structure, the binary tree, and precisely in this case, uh, the the platform it guarantees that the input is a binary search tree, where all the items in the left subtree of a node, it's smaller than the root, and all the so I mean is greater than the root, and all the items in the subtree that's first left of the root is smaller than the root node value itself, right? And recursively, the same criteria hold for all subtree as well. So that's why it's binary search tree. You can see that in the example. Now, how you can do this, right? So as I described the solution verbally, we want to iterate this data structure simultaneously from the start as well as from the end. So in this case, we want to scan this binary search tree from the left as well as from right, so that we have, like, uh, the left pointer pointing to the leftmost item in this binary search tree, right pointer pointing to the rightmost node in the binary search tree, and then shuffling this iterator would take the left pointer to the next bigger values, as well as to the next smaller value, as well as shuffling the right pointer should take this should take us to the next bigger value, right? So we want to have an iterator designed like that for binary search tree. So at a very high level, let's slide uh, the code skeleton. we want to make sure this is a picking iterator. So any call to the pick function will give us the next item that this iterator is pointing to. So if this is a BST iterator, so we want to return a tree node itself. So now what we want to do here, what we really want to do here is we want to have two iterator, head and tail iterator. So how we are going to initialize this, we'll come back to that. The initialization is not yet done. I'll come back to that. But let me first write a very high level template code to find the two sum in this given input. So while both of these iterator, uh, we want to pick both the nodes pointed by head and the tail iterator. Now we want to take the sum of the value in those two nodes, and if its target, that's return. But more importantly, if these two nodes collide, like that's a crossover point. So if n1 equals n2, which is going to happen at some point if we never find them, if we never find two nodes that sums up to the target, then that's like we can break this loop at this point, right? Now, otherwise, we compare the sum. If that's equal to target, we found two nodes summing up to target. Else, if sum is less than target, if sum is less than target, we want to increase the sum so that we shuffle the head iterator, right? So we move to the next bigger items. We can move the head iterator, else we move the tail iterator. In any other case, what we want to do is, if we come out of the loop, we can just return false, because that's the case we never encountered any two nodes that sums up to the target. All right. So this is the high level template. Now the main part is, or the core of the problem is, how do we write this iterator? And how do we make sure that we make it the hell and the head and the tail iterator so that we are iterating similarly in two different directions? Right. First of all, let's focus on how do we write an iterator so that we traverse from smaller item uh, to the large item, from the smallest item to the largest items in this BST. And that's basically how we write an in order, how we do an in order traversals from leftmost node to the rightmost node, right? So you see, how do we do in order traversals? We go to the root, we visit the whole entire left subtree, we come back to the root, visit it, and then we go to the entire right subtree and recursively do the same thing for each subtree as well, right? But how do we transform that recursive approach into an iterative one? So let's take this tree as an example, and maybe I will explain the algorithm, putting some comment. I'm at line number 27, so let's see how we can do that. Right. So you are in a current state. Let's say we start from the root. Our current root is 5 right now. So we are at root. What do we want to do? We want to visit the left subtree, right? So when we go to the left subtree, we want to make sure like we save the current state so that we come back and visit it. The right way to do this, if we are not using recursion, is make use of the stack. So when we go left of 5, we move to 3, but make sure like we push the current state 5 into the stack so that we come and visit it later. Now you are at 3, you go further left of it, that is 2, right? But when you go to the left, you make sure you save your current state so that you can come back and visit it. Now you are at 2, you go further left, which is null, nothing left of 2 exists, but you are also saving the current state. Now we are in a case where we don't have any state. Our current state is null, but we have some entry in the stack, right? So this is the point where we found the next item to uh, next smaller items in the whole given data structure. So that is currently the top of the stack, which is 2, which will pop out. But since that we pop out this item, we are not yet sure if we have traversed all the right subtree of this particular node, right? So we go towards the right of 2, which is still null, right? So now again our current state is null, but we have some entry in the stack. So this is a point where we identified the next smaller items in our data structure, which is on top of the stack 3. And again, like I said earlier, we are not yet sure if we have visited all the right subtree of this node 3. The right of this node is 4. So that's the new state, right? Now again, repeating the same approach, visit the entire left subtree. The current state is 4. So go to left of 4, which is null, but make sure you push the current state so that you come back and visit it later. So we are in a state where we have the current state as null, but there is some entry in the stack. So we found the next item to be displayed, which is 4. But we are not yet sure if we have visited all the right subtree of 4. So right of 4 is null again. Right. Now, our state is null, root is null, but our stack has some entry. So it is again the point where we pop the stack as the next bigger item, next smaller item in our given data structure. So the next in order item of the given BST, which is 5, right? Which is 5, but we are not yet sure if we have visited all the right subtree of 5. So we change the current state to the right of 5, which is 6. Taking the similar repeated approach, we have to visit all the left subtree of this newly explored node, which is null, which is null, but at the same time, we want to make sure we set the current state and stack so we come back and visit it later. Now our current state is null, stack had some entry, which is the point to pop the stack out to fetch the next in order item or the next bigger item in this BST, which is 6. We pop this item, but we are not yet sure if we have explored all the right subtree of 6, so we update the current state to the right of 6, which is 7. And this goes on, right? So our current state is not null. We want to make sure we visit all the left subtree of it. So we put this as null, but make sure we save it in the stack so that we come back and visit it later. Current state is null. Stack had some entry, time to pop out for the next in order item. 7 is popped out. Now our stack is empty. There is nothing right of 7. So our current state is null, our stack is empty. So this guarantees that we scan all the items in our binary search tree and we have found the right in order traversal for all the data in the tree. So let's see how we can do this. We just want to transform the approach what I just described and capture that logic into this method, right? So whatever is the next item, we want to save it in a state. Let's say next. So our pick is like return next. Our has next has to be next should not be null. If next is null, then we don't have any item to scan or iterate. But the difficult part is the move, right? So now that this is a iterator class, what we want to do is we want to define a constructor here, which takes tree node, right? So okay, this is the state here. A root can be the current state, what I described in our algorithm earlier. So now the main goal would be to write the move method, right? What should we do here? So while our stack is not empty, when are we proceeding? Stack should not be empty or our current state should not be null. Then what we need to do, if our current state is not null, then we want to make sure before we change our state to the left of what current is, we want to push this state into our stack. Now, and then we move towards the left. I haven't defined stack as of now, so let's have it. Else. So whatever the next top of the stack is, actually it should not be else, it has to be else if the stack is not empty. So if we pop items from the stack, we are not yet sure we have explored the right subtree of the current node. So what do we need to do here? Root has to be, because root has to be the right of the current right of the next item that's currently popped out, right? And then since that we are not scanning the entire tree, we are writing an iterator, we can just break it here so that when we call the move method next time, uh, we'll repeat the same. Now that we have has next, pick, and move method, when we instantiate this iterator, we need to make sure like we set next with the appropriate node. So we need to call this move method once during the instantiation, and after that if you use has next and pick method to do an iteration, then everything will be fixed. So you'll get the right next item to iterate, right? Okay, so this is, there's some typo here. Okay, now as of now we still have a stop code. Our code is not yet complete. How do we instantiate the iterator here, right? So if you see this, this iterator holds true for iterating from left to right. What we want to do if we want to iterate from right to left for the tail iterator, shall we just replicate this code and make a symmetrical change? Like a symmetrical change for that would be, instead of going towards the left, we go towards the right. And similarly, once we pop the item from the stack, instead of going to the right, we go to the left, right? So if you pause this video for a little bit, take the same input as an example and try to take an iterative approach going from bigger items to the smaller, then you'll be convinced. Symmetrically changing this left to right and right to left would solve the problem for you. But shall we just replicate the code for that? And I would say no. With simple change here, you can reuse the same code, right? What I want to do here is I would, instead of like doing calling the left and the right references from the node itself, I would get the left and the right child uh, with the functions that's provided. So I'll try to have a function that will help me fetch the left and the right child. A function which takes a tree node and returns a tree node. So how am I going to use this? I'm just going to show you this in a little bit. Okay, this dot left is left. That's all this typo here. And instead of doing root equals to next dot right, I will call this function right and apply this in next. This is doing the same thing. And similarly, doing the root dot, instead of doing root dot left, I would call this left function in a root. Now, how I'm going to use this to instantiate an iterator is I would define two functions. I'll define two functions, left and right here. So the role of the left is you are given a node, you want to return node.left. And for the right, you are given a node, what you want to return is node.right. Now, what are you going to do with the head iterator? So head iterator has to be, it has to stand from left to right, right? So BST iterator, I provide root, left and right, okay? And for tail iterator, it has to go from right to left. If you just flip left to right and right to left, it is going to do it for you. If you just pause this video and think out loud, you'll find very satisfied with yourself, like how this piece of abstraction is working here, right? Hopefully, if we haven't missed anything, this should work. So let's just clean it up a little bit and let's run it. So this works. If we submit it, this is accepted. I hope you had fun. This problem is tagged as late code easy, but I feel this is more involved and it has to be a medium level question. If you just take a simple approach, doing in order traversal, saving all the nodes in an array, then you can just go with an array approach. But that way, you are scanning the entire tree, saving that in an array, right? And then again, you are scanning the same array. So you are doing like twice an iteration. This is saving one iteration for you. And if the tree is balanced, then the total memory uses what you are doing is on the order of log n. But worst case, if the tree is pretty much skewed on the one side, the size of the stack grows proportionally to the size of the tree, which is going to be an on space complexity. But from the time complexity, this is saving a second iteration of the tree. So we are simply visiting every node just once, and this is a ON solution. I hope you enjoyed it and you have a nice rest of the day. Thank you.